The sun just did something terrifying. A vast hole ripped across its surface, unleashing a river of plasma at Earth. And at that exact moment, the interstellar visitor Comet 3I Atlas vanished from every telescope, and Mother Earth experienced an earthquake. Now the question on everybody's mind is what happened. Was it destroyed or transformed? And what might it look like when it re-emerges, if at all it will? As one comet slips into hiding, another bursts into the spotlight. Comet Lemmon, an icy relic older than civilization itself, is racing across our skies. We tell you why the next 2 weeks are going to be crucial. Meanwhile, in China, physicists have achieved what sounds like pure science fiction, an unhackable communication network that is a total snitch. And don't blink, because before we close, we'll reveal the cosmic dates you cannot miss, including one no one is talking about, yet should. If these mysteries have you on edge the way they have me, don't just watch, take action. Hit like, smash subscribe, and stay locked in as these stories unfold in real time. Drop a comment with where you're watching from, what time it is there, and tell me straight, do you believe we're being told the whole truth about these world-shifting discoveries? And if you want to help this community grow, share this video on X, Facebook, Reddit, or even your group chats. Every share, every comment, every click is fuel for the hunt. You're the reason we can keep chasing these stories. So thank you for standing with us in the search. Part 1, the disappearance. The sun just did something terrifying. October the 2025 arrived with a cosmic alarm bell that most people never heard. Scientists monitoring our star watched in growing unease as a massive transequatorial coronal hole ripped open across the solar surface, a gash in the sun's magnetic field that looked like a wound bleeding invisible energy into space. This wasn't your typical solar activity, the kind that produces pretty auroras and maybe disrupts a few satellite signals. The hole was enormous, spanning regions of both the northern and southern solar hemispheres simultaneously, a configuration that happens rarely, and with consequences we're only beginning to understand. The solar wind that poured through this tear in the sun's magnetic armor reached speeds of 700 kilometers per second. To put that in perspective, imagine a hurricane where every particle of air is moving at nearly 1.5 million miles per hour. The stream of charged particles, protons and electrons stripped from their atoms, came screaming toward Earth like a cosmic fire hose aimed directly at our planet's magnetic field. The alignment was perfect, almost suspiciously so. The magnetic polarity of the solar wind matched Earth's field orientation in precisely the configuration needed for maximum coupling, the strongest possible transfer of energy from the sun's breath into our planetary magnetosphere. Geophysicists scrambled to predict the impacts. Power grid operators received warnings. Satellite controllers prepared for possible malfunctions. The aurora chasers packed their cameras and headed north, knowing this kind of solar assault would paint the sky in colors that defy description. But something else happened at that exact moment. Something that would turn this solar event from a routine space weather episode into a genuine cosmic mystery. Comet 3I Atlas, only the second confirmed interstellar visitor ever detected in our solar system, disappeared behind the sun. One moment it was there, a faint smudge of light moving on an orbit that originated in another star system, carrying ice and rock that formed in alien clouds around a sun we'll never see. The next moment it vanished into the solar glare, swallowed by the overwhelming brightness of our star, rendered invisible to every telescope on Earth and in space. The timing was impossible to ignore, Earth's magnetic field getting hammered by the fastest solar wind in months, and simultaneously, our only accessible interstellar messenger going dark behind the very source of that assault. Scientists are careful people, trained to avoid jumping to conclusions, conditioned to repeat the mantra that correlation does not equal causation. They measured their words carefully when reporters asked if these events could be connected. Then the earthquake started. Multiple magnitude 7 earthquakes struck different regions of Earth within hours of the solar wind's arrival. Seismometers recorded the violent shaking, the sudden release of tectonic energy that had been building for years, perhaps decades, in the stressed rock beneath our feet. The tremors were not unexpected in a statistical sense. Earth experiences roughly 15 magnitude 7 earthquakes every year on average. But having several occur in close temporal proximity to a major solar event, and the disappearance of an interstellar comet, triggered something in the human pattern recognition system, that ancient part of our brains that searches for connections, that demands meaning from coincidence. Could the sun's magnetic assault on Earth have somehow triggered seismic activity? The mainstream scientific consensus says no, that's not how earthquake physics works. Tectonic plates don't care about magnetic fields or solar wind. They grind and slip according to the laws of rock mechanics and accumulated strain energy. But there are other voices, researchers working at the fringes of geophysics, who point to statistical anomalies in earthquake timing during solar maxima, who suggest mechanisms involving ionospheric coupling or subtle changes in Earth's rotation rate. These ideas haven't gained traction in peer-reviewed literature, but they circulate in conference hallways and online forums. Whispered possibilities that the mainstream hasn't yet disproven to everyone's satisfaction. The comet, though, that's where the real mystery lives. 3I Atlas earned its designation as the third confirmed interstellar object detected passing through our solar system. The first was Yawn/Oumuamua in 2017, a bizarre elongated thing that tumbled through the inner solar system and exhibited acceleration that couldn't be fully explained by normal comet outgassing. The second was 2I/Borisov in 2019, which looked and behaved more like the comets we're familiar with, a reassuring ball of ice and dust that followed predictable physics. 3I Atlas was discovered in 2025, tracked as it fell toward the sun on a hyperbolic orbit, moving too fast to be bound by our star's gravity, clearly a visitor just passing through on its way back to interstellar space. These objects are incredibly precious to science. They're the only samples we have of material from other stellar systems, at least until we develop the technology to send probes to nearby stars and return with physical specimens, something that won't happen in any of our lifetimes. Every photon of the light we collect from an interstellar comet carries information about chemistry, about the composition of protoplanetary disks around other suns, about whether the processes that formed our solar system are universal or unique. When 3I Atlas disappeared behind the sun, we lost our ability to gather that data, at least temporarily. The question that haunts astronomers now is simpler and more disturbing than any of the speculation about solar, wind, or earthquakes. When 3I Atlas emerges from behind the sun, if it emerges at all, will we recognize what comes out? Did the sun just eat our interstellar visitor? Could the intense heat and radiation and magnetic turbulence near our star have reshaped it, broken it apart, vaporized it entirely? We're about to find out, and the answer might upend everything we think we know about these alien wanderers. Part 2, The Traveler We Lost. The story of 3I Atlas begins like most comet discoveries do, with patience, with automated telescopes scanning the sky night after night, looking for anything that moves against the background stars. The Atlas survey, short for Asteroid Terrestrial Impact Last Alert System, consists of 4 robotic telescopes distributed around the globe, designed primarily to spot asteroids that might pose a collision threat to Earth. But the telescopes don't discriminate. They capture anything that moves, including comets, and in the early months of 2025, they captured something extraordinary. The object appeared first as a faint streak in images from the Hawaiian stations. Follow-up observations from other facilities confirmed it was moving, and moving fast. Trajectory calculations revealed the telltale signature of a hyperbolic orbit, an eccentricity greater than 1, meaning this thing wasn't bound to the sun. It came from somewhere else, and after its close approach to our star, it would leave, headed back into the cosmic ocean between stars. The orbital energy was wrong for a solar system native. This was interstellar. The astronomy community mobilized quickly. Telescope time, always scarce and competed for months in advance, was suddenly made available. Spectroscopy, the analysis of the light reflected or emitted by the comet, became the priority. What was this thing made of? Did it contain the same mix of water ice, carbon dioxide ice, and organic molecules that characterize comets born in our solar system? Or would its composition reveal alien chemistry, ratios of elements that pointed to formation conditions around a different type of star? Early data suggested something puzzling. The brightness of 3I Atlas didn't behave quite like astronomers expected. Comets typically brighten as they approach the sun, following a predictable curve related to the increasing sublimation of ice as solar heating intensifies. Water ice starts subliming, turning directly from solid to gas, when sunlight warms the surface to around 200 degrees Kelvin. Other volatiles, like carbon monoxide and carbon dioxide, sublimate at even lower temperatures, creating activity at much greater distances from the Sun. The brightness curve of 3I Atlas showed flattening periods where the comet didn't brighten as much as models predicted, followed by sudden jumps in luminosity that suggested discrete outbursts of dust or gas. The coma, the fuzzy cloud of gas and dust surrounding the nucleus, appeared unusually faint in some observations. Dust production seemed lower than expected for a comet of its size. Some researchers speculated the nucleus might have an unusually high density, more rock than ice, which would explain the weak activity. Others suggested the opposite, that the nucleus was extremely porous, almost like a rubble pile held together by weak gravity, and that this structure was causing the ice to sublimate in unpredictable bursts rather than steadily. Then there were the non-gravitational forces. Comets don't follow pure Keplerian orbits determined solely by the Sun's gravity. When ice sublimates from the nucleus, it creates jets of gas that act like tiny rocket engines, pushing the comet slightly off its predicted path. These non-gravitational accelerations are small but measurable, and they introduce uncertainty into predictions of exactly where a comet will be at any given time. For 3I Atlas, these perturbations were particularly difficult to model. The orbit calculations kept getting refined, the error bars kept shifting, and astronomers grew increasingly uncertain about precisely when and where the comet would reappear from behind the Sun. Some observations hinted at possible fragmentation before the disappearance. Comet nuclei are fragile things, weakly bound collections of ice and rock that can split apart under thermal stress or tidal forces. When a comet fragments, it often creates a train of smaller pieces following similar orbits, sometimes visible as multiple condensations in the coma. Imaging of 3I Atlas showed possible asymmetries, elongations that might indicate the nucleus was beginning to come apart. If the comet was already fragmenting before it disappeared, the question becomes even more pressing. What will emerge from the solar glare might not be a single object but a stream of debris, or perhaps nothing at all if the fragments became too small to detect. The comparison to previous interstellar visitors was inevitable. 1I/Oumuamua, that first detected interstellar object, was never confirmed to be a comet. It showed no visible coma, no dust tail, nothing that would definitively identify it as an icy body. Yet it accelerated away from the Sun in a manner that couldn't be explained by gravitational forces alone. The most likely explanation remained comet outgassing, but of a volatile more exotic than water, possibly carbon monoxide or molecular nitrogen, substances that would sublimate without producing visible dust. The alternative explanations from light sails to alien probes captured public imagination, but found little support among scientists who deal in evidence rather than speculation. 2I/Bursov behaved more like a familiar comet, with a proper coma and tail and brightness variations that match standard comet models reasonably well. Its spectrum revealed water vapor and carbon monoxide, chemistry similar to what we see in solar system, comets. This was reassuring in a way. It suggested that planetary formation around other stars follows similar rules, produces similar objects. But Borisov also showed signs of fragmentation near perihelion, its closest approach to the Sun. Images captured what appeared to be a small chunk, breaking away from the main nucleus. A reminder that these interstellar travelers don't always survive their passage through the inner solar system intact. Now 3I Atlas was following a similar path, diving toward the Sun, and we'd lost sight of it at the worst possible moment. The geometry of solar conjunction, when an object passes behind the Sun as seen from Earth, creates an observation gap that can last days or weeks depending on the object's trajectory and brightness. For a faint comet already showing signs of unusual behavior, this gap becomes a black box, a period where anything could happen and we'd have no way to know. The comet could be disintegrating, it could be brightening dramatically, it could be intact and simply too close to the Sun's glare to see. We wouldn't know until it emerged, if it emerged. Models attempted to predict what would happen based on assumed nucleus sizes and compositions. If the nucleus was large and mostly rocky, thermal models suggested it would survive with minimal mass loss. If it was small and icy, the heat near perihelion could vaporize it completely, leaving nothing but a dispersing cloud of gas and dust. The uncertainty in nucleus size was enormous, ranging from a few hundred meters to several kilometers, a factor of 10 or more, and that uncertainty propagated through every prediction model, turning forecasts into guesswork. The phrase astronomers kept using was invisible interstellar traveler. Somewhere behind the sun's glare, hidden from every telescope humanity has built, an object from another star system was either surviving or dying, and we could do nothing but wait and wonder what would emerge when the geometry finally allowed observation again. The wait felt like an eternity compressed into days. Part 3, when solar wind meets alien ice. The sun is not a gentle thing. We think of it as our benign, life-giving star, the warm light that makes Earth habitable. But up close, the sun is violent, chaotic, a roiling ball of plasma where temperatures reach millions of degrees and magnetic fields twist into configurations that store energy like loaded springs. When those springs snap, the results can be catastrophic for anything nearby. The coronal hole that opened in October 2025 was one of those events that make solar physicists nervous. Coronal holes are regions where the sun's magnetic field opens up into space rather than looping back to the surface. These open field lines act like highways for solar wind, allowing plasma to escape into the solar system at high speed. A typical solar wind speed is around 400 kilometers per second. The wind, pouring from this particular coronal hole, was moving at 700 kilometers per second, nearly twice as fast, carrying more momentum, more energy, more potential for disruption. When solar wind at those speeds encounters a comet, the interaction becomes complex and violent. Comets are not magnetically shielded like Earth. They don't have a magnetosphere to deflect the charged particles. Instead, the solar wind slams directly into the coma, the cloud of gas and dust surrounding the nucleus, and strange physics takes over. The gas in the coma becomes ionized by solar ultraviolet radiation, creating a population of electrically charged molecules. These ions respond to magnetic fields, and the solar wind carries frozen-in magnetic field lines that drape around the comet like a cape. The result is a magnetotail, a structure formed by the interaction between the solar wind's magnetic field and the ionized gas from the comet. This tail can extend millions of kilometers downstream, away from the sun, glowing faintly in the light of ionized carbon monoxide and other molecules. The tail is not a passive structure. Turbulence in the solar wind causes the tail to wave and flutter. Disconnection events can occur where the tail breaks off entirely and a new one begins to form. These interactions are visible from Earth with the right instruments, and they provide clues about both the solar wind conditions and the comet's gas production rate. But what happens when a comet encounters an exceptionally fast solar wind while already stressed by intense solar heating near perihelion? History provides some terrifying examples. Comet Eason, discovered in 2012 and predicted to become spectacularly bright, disintegrated during its close pass by the sun in 2013. Images from solar observing spacecraft showed the comet entering the perihelion region as a bright object and emerging as nothing but a dispersing cloud of dust. The nucleus apparently broke apart completely, unable to withstand the thermal and tidal stresses. Comet Lovejoy, a sun grazer that passed within 140,000 kilometers of the solar surface in 2011, somehow survived despite predictions it would be destroyed. Images captured the comet's tail extending millions of kilometers off to perihelion, fed by massive gas production from the superheated nucleus. The survival of Lovejoy was unexpected and still not fully explained. Some combination of nucleus size, composition, and structural strength allowed it to endure heating that should have vaporized it entirely. 3I Atlas was not passing as close to the sun as those extreme sun grazers, but it was entering the region where solar influence becomes dominant, and it was doing so during a period of unusually intense solar wind. The question became whether the combination of factors, thermal stress plus radiative heating, plus solar wind pressure, plus possible prior fragmentation, would be enough to destroy it. Some researchers proposed more exotic interactions. The electric comet model, promoted by a small group of plasma physicists, suggests that comets develop electrical charges as they interact with the solar wind, and that electrical forces, not just thermal sublimation, drive comet activity. Mainstream astronomy has not embraced this model, finding that conventional physics explains observations adequately without invoking electrical effects. But proponents point to phenomena like disconnection events in comet tails and rapid brightness changes as evidence that electrical processes play a role. The hypothesis extends further into fringe territory, with suggestions that strong solar wind events could induce charge separations in a comet's coma that might, under certain circumstances, cause explosive disruptions or trajectory changes beyond what's expected from simple outgassing. The evidence for these claims is contested, the theoretical framework incomplete, but the ideas circulate because they attempt to explain observations that don't quite fit standard models. When 3I Atlas disappeared during a major solar wind event, those promoting electric comet models saw potential confirmation of their ideas. Mainstream astronomers saw an unfortunate but ultimately coincidental overlap of events. What makes the situation more uncertain is that we don't actually know what 3I Atlas is made of. Spectroscopic observations before the disappearance were limited and didn't provide a complete compositional inventory. The comet could be water ice dominated like many solar system comets. It could be carbon monoxide ice dominated, which sublimates at much lower temperatures and could drive activity at greater distances from the sun. It could be rich in silicates and poor in volatiles, more like an asteroid than a typical comet. Each composition would respond differently to solar heating and solar wind interaction. If the nucleus is extremely porous, almost like aerogel with density barely higher than the gas in the coma itself, thermal waves would penetrate deeply, heating subsurface ice and potentially causing the entire structure to disintegrate in a cascade of sublimation. If the nucleus has an insulating dust mantle covering most of its surface, gas production would be concentrated in a few active areas, creating jets that could spin up the nucleus or torque its rotation in unpredictable ways. If the nucleus is a contact binary, two lobes held together by weak gravity, tidal forces and thermal stress could pull it apart. The sun, in this scenario, becomes a kind of cosmic gatekeeper, a destructive force that tests every object passing through the inner solar system. Interstellar comets, having formed in different environments with possibly different structural properties, and solar system comets might be particularly vulnerable, or they might be more robust, forged in conditions that made them tougher. We won't know until we see what emerges. The comparison to Comet Shoemaker Levy 9 is instructive. That comet was torn apart by tidal forces during a close pass by Jupiter in 1992, breaking into more than 20 fragments that later crashed into the planet in a spectacular series of impacts. The tidal disruption happened because Jupiter's gravity gradient across the comet's diameter exceeded the comet's own self-gravity, literally pulling it apart. The sun's tidal forces are much weaker at the distance where 3I Atlas passed, but a comet already weakened by thermal stress or prior fragmentation might succumb to forces that a healthy nucleus would easily resist. Did the sun just reveal something terrifying about interstellar visitors? The answer depends on what we see when the comet emerges from conjunction. If 3I Atlas reappears intact, continuing on its hyperbolic trajectory with normal gas and dust production, the solar wind event becomes a footnote, a coincidence that sparked speculation but ultimately meant nothing. If the comet has disintegrated or vanished, we're left with haunting questions about whether interstellar objects are fundamentally more fragile than our models assume, whether there's something about their formation or structure that makes them vulnerable to solar assault in ways we didn't predict. Part 4. The vigil begins. Astronomers are marking calendars, checking ephemerides, preparing observation plans for the moment when 3I Atlas should become visible again. The timeline depends on several factors, including the comet's exact trajectory, which is uncertain due to non-gravitational forces, its brightness, which could have changed dramatically, and the observing geometry, which determines how far from the sun the comet needs to be before telescopes can detect it against the sky background. Current predictions suggest the comet should emerge from solar conjunction in late October or early November 2025. Reaching sufficient solar elongation, the angular separation from the sun as seen from Earth, to be observable with specialized equipment. Initial recovery attempts will likely use space-based observatories that can block the sun's light more effectively than ground-based telescopes. SOHO, the Solar and Heliospheric Observatory, has coronagraphs designed to create artificial eclipses, allowing observation of the region close to the Sun where comets often hide. STEREO, the Solar Terrestrial Relations Observatory, consisting of 2 spacecraft in solar orbit, provides different viewing angles that might catch the comet earlier than Earth-based observations. The Parker Solar Probe, humanity's closest approach to the Sun, follows an orbit that periodically brings it within the orbit of Mercury, through regions where solar wind speed and temperature reach extreme values. If the probe's trajectory happened to pass near 3I Atlas during the conjunction period, its instruments might have captured data about the comet in conditions no Earth-based telescope can observe. The Parker science objectives focus on the solar corona and solar wind, not comets, and unless the comet happened to be in the probe's narrow field of view at the right time, we'll have no data from that critical period. Mission scientists have not announced any fortuitous encounters, suggesting the geometry didn't align, or that the comet was too faint for Parker's instruments to detect against the bright solar background. What will the first recovery images show? Best case scenario, the comet appears as expected, perhaps slightly fainter due to dust loss but otherwise intact, with a visible coma and tail indicating active sublimation of ice from the nucleus. The spectral signature would show familiar lines of water vapor, cyanogen, carbon monoxide, the molecular fingerprints that confirm comet composition. The tail length and structure would provide information about gas production rate and solar wind conditions in the post-conjunction period. Astronomers would measure the brightness, compare it to pre-conjunction values, and assess whether the comet lost significant mass during its closest approach to the Sun. Worst-case scenario, nothing appears. The sky remains empty where 3I Atlas should be, suggesting complete disintegration. The nucleus fragmented into pieces too small to detect individually, or vaporized entirely, leaving only a dispersing cloud of gas that's too diffuse to show up as a distinct object. This outcome would be disappointing scientifically, but not unprecedented. Several comets have disappeared after close solar approaches, and their loss becomes a data point in our understanding of comet fragmentation physics. Between these extremes lie numerous possibilities. The comet could return as multiple fragments, a string of condensations along the orbit indicating the nucleus split but the pieces survived. Fragment streams are difficult to observe because each individual piece is fainter than the original nucleus, but they provide valuable information about nucleus structure and the mechanics of breakup. If 3I Atlas returns as fragments, analysts would measure the separation distances and velocities to reconstruct when and how the breakup occurred. Another possibility is dormancy. The comet could have exhausted its near-surface volatiles during the close solar pass, leaving a darkened crust that prevents further sublimation until solar heating cracks the crust or erosion exposes fresh ice. Dormant comets look like asteroids, showing no coma or tail, just a bare rock reflecting sunlight. If 3I Atlas goes dormant, we'd lose our ability to study its gas composition, but we'd gain information about surface processes and the formation of insulating mantles. The most intriguing scenario involves unexpected brightening. Sometimes comets fragment in ways that expose fresh, volatile-rich material to sunlight, causing sudden increases in gas production and brightness. A fragmenting nucleus can create new active areas, increasing the total sublimating surface area. If 3I Atlas fragments and brightens simultaneously, the comet that emerges might be more spectacular than the one that disappeared, though in fragmented form it would likely fade quickly as the small pieces deplete their ice reserves. Spectral diagnostics will be critical. Observations before conjunction showed the typical signatures of water and perhaps carbon monoxide, but a complete spectral inventory was never obtained. Post-conjunction spectroscopy might reveal species that weren't detected earlier, either because the comet wasn't producing them in significant quantities, or because we weren't looking at the right wavelengths. Oxygen emission lines would indicate water sublimation. CN, cyanogen, points to carbon-nitrogen chemistry. Sodium and ion lines sometimes appear in comets and can indicate exposure of metallic-rich material from the nucleus interior. Amateur astronomers have a role to play in the recovery effort. A network of backyard telescopes distributed globally provides continuous sky coverage that professional facilities, with their limited observing time and scheduled programs, cannot match. If 3i Atlas brightens unexpectedly or fragments into widely separated pieces, amateur observers might be the first to notice. Crowdsourced astronomy has become increasingly important as digital cameras and software make it possible for dedicated amateurs to produce observations rivaling professional quality. There's a live cosmic mystery unfolding in real time, and everyone with a telescope and clear skies can participate. The comet could reappear at any moment, assuming it survived. Or days could pass, then weeks, with nothing visible, until astronomers reluctantly conclude that 3i Atlas is gone. Destroyed by the sun it came so far to visit. The uncertainty is maddening and exhilarating in equal measure. We sent no probe to intercept the comet. We have no way to actively search for it beyond pointing our telescopes at the predicted location and waiting. All we can do is watch and wonder and prepare for whatever emerges from the solar glare. The broader question haunts the astronomical community. If the nucleus is gone, do we still have 3i Atlas? Or is it just debris now, a dispersed cloud of dust and gas that once was an interstellar comet, but no longer qualifies as a discrete object? Philosophically, it echoes the ship of Theseus' paradox. If every plank of a wooden ship is replaced over time, is it still the same ship? If a comet fragments into 1,000 pieces, each piece following nearly the same orbit, carrying material from the original nucleus, are they collectively still the comet? Or has the comet ceased to exist? There's no formal definition that resolves this question. It's a matter of convention and convenience, and different researchers will answer differently depending on their perspective. But the question matters because 3i Atlas represents something precious and irreplaceable, a sample of another star system, and losing it feels like more than just losing an astronomical target. It feels like losing a connection to something vast and distant, a thread linking us to the wider galaxy that got severed before we could fully grasp what we held. Part 5. When coincidence becomes conspiracy. Why does any of this matter beyond the narrow confines of planetary science journals and astronomy conferences? Because humans are pattern-seeking creatures who evolved to find meaning in correlation, to see connections even where none exist, and the simultaneous occurrence of a major solar event, the disappearance of an interstellar comet, and multiple large earthquakes on Earth, triggered every alarm in our collective unconscious that screams, something is happening. The mainstream scientific position on solar-terrestrial earthquake connections is clear and unambiguous. Earthquakes are driven by plate tectonics, by the slow, inexorable motion of lithospheric plates riding on the convecting mantle, by accumulated strain energy in the crust that eventually exceeds the frictional resistance holding faults locked. Solar activity has no plausible mechanism to trigger this release. Magnetic fields don't affect rock. Solar wind particles don't penetrate to the Earth's surface. They're stopped by the magnetosphere and atmosphere. The thermal energy delivered by solar radiation is negligible compared to Earth's internal heat. Every analysis of earthquake catalogs looking for correlations with solar cycles or individual solar events has found nothing beyond what would be expected by chance. And yet, the correlations keep appearing in data sets, tantalizing patterns that don't quite reach statistical significance but don't quite disappear either. Some researchers, working at the margins of respectability, continue to explore possible mechanisms. Could ionospheric disturbances caused by solar activity affect the electrical properties of fault zones? Could subtle changes in Earth's rotation rate or magnetic field orientation, driven by solar wind momentum transfer, modulate tectonic stress at levels too small to measure directly, but sufficient to tip a fault that's already near failure? Could that be magneto-hydrodynamic coupling between the ionosphere and conducting layers in the crust that transmits energy in ways we don't yet understand? These ideas face enormous skepticism because extraordinary claims require extraordinary evidence, and the evidence remains circumstantial at best. But the human mind doesn't operate on statistical significance thresholds. It operates on narrative, on stories that connect disparate events into coherent wholes. When the sun attacks and earthquakes strike, and a comet vanishes all in the same news cycle, the narrative writes itself even if the physics doesn't support it. The interstellar nature of 3I Atlas adds another layer of mystery and speculation. These objects come from outside our solar system, from environments we can barely imagine, formed from materials whose composition and isotopic ratios might differ from solar system norms. They're literally alien in the most precise sense of that word. And humanity has always projected its hopes and fears onto the alien and unknown. When Oumuamua exhibited acceleration that couldn't be immediately explained by standard comet outgassing, speculation erupted about artificial origin, about alien probes conducting reconnaissance, about technologies beyond our understanding. The simplest explanation remained natural processes, but the alien probe hypothesis captured public imagination because it satisfied narrative needs that dry scientific papers about carbon monoxide sublimation could never touch. 3I Atlas disappearing during a solar storm invites similar speculation. Did the comet carry something, encode something, that made it a target? Are we witnessing a cosmic quarantine protocol? The sun destroying potential threats from interstellar space before they can penetrate the inner solar system? The scientific absurdity of these ideas doesn't diminish their psychological appeal. We want the universe to contain mysteries deeper than orbital mechanics and spectroscopy. We want hidden meanings behind celestial alignments. We want comets to be more than dirty snowballs. We want them to be messengers, carriers of information, or life or purpose. The panspermia hypothesis, the idea that life spreads through the cosmos on comets and asteroids, provides a scientific veneer for these desires. If comets carried the organic precursors that led to life on Earth, delivered during the heavy bombardment period billions of years ago, then every comet becomes a potential seed carrier, and interstellar comets become particularly precious because they might carry chemistry from biospheres around other stars. The destruction of 3I Atlas, if that's what happened, becomes the destruction of a biological sample, a library burned before we could read its contents. More exotic possibilities circulate in fringe communities. Electric universe proponents see the sun's interaction with the comet as evidence of plasma physics. They claim mainstream science ignores. They point to the comet's unusual brightness variations, to the strong solar wind, to disconnection events in other comet tails, and argue these phenomena require electrical rather than gravitational and thermal explanations. The mathematics of their models rarely withstand scrutiny. Predictions often fail to match observations, but the intuitive appeal of electricity as a universal force, the visual drama of lightning and sparks, gives electric universe ideas a persistence that transcends their scientific shortcomings. Conspiracies inevitably emerge. Are space agencies hiding data? From the Parker Solar Probe's close passes by the sun, did instruments capture images or spectra of 3I Atlas during the conjunction period that officials chose not to release? What would motivate such secrecy? Perhaps the comet exhibited behavior that couldn't be explained, that challenged fundamental assumptions, that frightened people who understood the implications. Perhaps it fragmented in a manner inconsistent with natural processes, or emitted signals, or changed trajectory in ways that suggested control. These scenarios are vanishingly unlikely, bordering on impossible, but absence of evidence becomes evidence of conspiracy in a minds predisposed to distrust official narratives. The psychological function of conspiracy theories is well studied. They provide control, or the illusion of control, in the face of random and chaotic events. They replace a universe of meaningless coincidence with a universe of hidden order and purpose, even if that purpose is malevolent. Better to believe in conspiracies than to accept that earthquakes strike randomly, that comets disintegrate without reason, that we're tiny specks of consciousness on a fragile world hurtling through an indifferent cosmos. The narrative of hidden knowledge and suppressed truth is more emotionally satisfying than the narrative of patient scientific investigation, slowly converging on tentative conclusions. But here's the thing. Sometimes the universe does align in ways that defy probability. Sometimes coincidences are too perfect to dismiss, even when we can't establish causation. The October 2025 conjunction of events, solar storm and comet disappearance and earthquakes, might be exactly that. A coincidence so improbable that it demands our attention even if ultimately it means nothing. Or it might be the first hint of connections we don't yet understand. Weak couplings between geophysical systems and space weather that operate at levels below our current detection thresholds. Science progresses by investigating anomalies, not by dismissing them. The researchers exploring solar earthquake correlations are doing legitimate, if speculative, science. They'll probably find nothing, but the search itself is worthwhile. When 3I Atlas emerges from behind the sun, if it emerges, we may not recognize it. The comet that went in might not be the comet that comes out. And when astronomers publish their analyses of what they observe, when they present explanations grounded in physics and chemistry and orbital mechanics, some people will accept those explanations and move on. Others will continue searching for hidden meanings, for connections between the comet and the earthquakes, and the solar storm that transcend material causation. Both responses are human. Both reflect deep needs to make sense of our place in a cosmos that offers more questions than answers. The sun did something terrifying, and a comet vanished, and the earth shook, and whatever truth underlies those events were left with wonder and unease in equal measure. Pot 6, the comet we can see. While 3I Atlas plays hide-and-seek behind the sun, another comet is putting on a show you can actually watch, assuming you know where to look and you're willing to wake up before dawn or stay up late after sunset. Comet C/2025A6, discovered by the Mount Lemmon Observatory in Arizona, and thus carrying the designation Lemmon, is approaching its own close encounter with the sun, and reaching brightness levels that put it within range of binoculars or small telescopes, possibly even naked eye visibility for observers under dark skies away from light pollution. The next 2 weeks represent the optimal viewing window. Lemmon's perihelion, its closest approach to the sun, is scheduled for mid-November 2025, but the geometry of its orbit brings it to maximum visibility from Earth, slightly before perihelion when it's still far enough from the sun's glare to observe comfortably. The comet is currently visible in the pre-dawn eastern sky, rising a few hours before the sun, glowing with the soft, fuzzy light, characteristic of an active comet with a well-developed comber and possibly a short tail. Current magnitude forecasts place Lemmon between magnitude 4 and magnitude 5, right at the threshold of naked eye visibility. The human eye can typically see objects down to magnitude 6 under good conditions. A magnitude 4 should be easily visible away from city lights, though pinpointing it without binoculars requires knowing exactly where to look. The comet is currently passing through the constellation Cancer, moving eastward against the background stars, and finder charts available online show its path relative to easily recognizable star patterns. Observing comets requires patience in dark skies. Unlike planets, which appear as distinct points or disks, comets are diffuse objects. Their light spread across an extended area. This diffuse nature makes them more sensitive to light pollution and sky conditions than compact objects of similar integrated brightness. A magnitude 4 comet will vanish completely in bright suburban skies, where magnitude 4 stars remain easily visible. Success requires traveling away from urban areas to locations where the Milky Way is visible overhead, where the sky darkness allows your eyes to detect extended low-surface brightness objects. Binoculars are the ideal instrument for comet observing. They provide enough magnification to concentrate the comet's light, while maintaining a wide field of view that makes finding and tracking the object easier. 7x50 binoculars, a common size owned by many amateur astronomers and nature observers, work particularly well. Mount them on a tripod if possible to eliminate handshake and allow longer viewing periods without fatigue. The comet will appear as a small fuzzy patch, distinctly non-stellar, possibly with a hint of green color from emission by diatomic carbon molecules in the coma. Telescopes can reveal more detail, showing the coma structure, any jets or fans of material emanating from specific active regions on the nucleus, and the tail if one has developed sufficiently. But higher magnification narrows the field of view, making the comet harder to locate initially and harder to keep centered as Earth's rotation carries it across the sky. Many experienced comet observers prefer binoculars for aesthetic reasons. The wide-field view shows the comet in context against star fields and the Milky Way, emphasizing its nature as a temporary visitor moving through more permanent celestial scenery. Early observations of Lemmon revealed something that makes comet scientists nervous and excited in equal measure. The brightness wasn't following prediction models perfectly. Comets are notoriously difficult to predict because their brightness depends on factors we can't measure directly, like the nucleus size, composition, rotation state, surface properties, and dust-to-gas ratio. Models make assumptions about these parameters based on statistics from other comets, but individual comets often deviate from average behavior. Lemmon showed periods where it brightened faster than expected, followed by plateaus where the brightness remained nearly constant despite decreasing distance to the Sun. These deviations could indicate several phenomena: outburst activity, where a sudden exposure of fresh volatile material creates a temporary increase in gas and dust production, can cause rapid brightening. Rotation of the nucleus bringing different hemispheres into sunlight, if one hemisphere is more active than the other, creates periodic brightness variations. Or, more ominously, the deviations could signal the early stages of fragmentation, where the nucleus begins to break apart under thermal or tidal stress. Fragmentation is the hidden danger that haunts every comet prediction. A comet can be brightening normally, following its expected curve toward perihelion, looking healthy in every respect, and then suddenly it starts to come apart. The process can be rapid or gradual. Sometimes a large chunk splits off and forms a separate condensation visible near the main nucleus. Sometimes the entire nucleus disintegrates into a cloud of small fragments that individually are too faint to see, but collectively can create a dramatic increase in total brightness as their combined surface area drives enhanced sublimation. The physics of fragmentation involves mechanical strength, thermal stress, and spin state. Comet nuclei are weak structures, more like compacted snow than solid rock, held together primarily by their own feeble gravity supplemented by tensile strength from ice sintering on possibly organic tars. When the Sun heats one side of the nucleus, thermal expansion creates stress. If the nucleus is spinning, centrifugal forces add mechanical stress, and jets create torques that can spin the nucleus up to faster rotation rates. At some point, the accumulated stress exceeds the material strength, and cracks propagate, and the nucleus splits. Lemmon's sublimation science adds another layer of complexity. The comet appears to be driven by carbon monoxide or carbon dioxide sublimation, as much as or more than water sublimation. These molecules are more volatile than water, meaning they turn from solid to gas at lower temperatures and greater distances from the Sun. A carbon monoxide-driven comet can be active far beyond the snow line where water ice remains frozen, producing a coma and tail while still in the outer solar system. As the comet approaches perihelion and temperatures rise, water sublimation eventually takes over, often creating a transition in activity patterns and brightness behavior. The tail interactions with solar wind provide another observational opportunity. Lemmon's ion tail, if it develops one, will point directly away from the Sun, blown by the solar wind like a wind sock. The dust tail follows a curved path particles pushed by solar radiation pressure, but retaining the orbital motion they had when released from the nucleus. These two tail types, ion and dust, often separate into distinct structures visible in photographs. The ion tail appears bluish from carbon monoxide ion emission, straight and sometimes featuring streamers and knots caused by magnetic field irregularities in the solar wind. The dust tail appears yellowish-white from reflected sunlight, broader and more diffuse, curving gently away from the nucleus. Comparing Lemmon to 3I Atlas highlights fundamental differences between solar system native comets and interstellar visitors. Lemmon formed 4.6 billion years ago in the disk of gas and dust surrounding the young sun, probably in the region beyond Neptune where temperatures were cold enough for water and other volatiles to condense as ice. Gravitational perturbations from the giant planets eventually scattered it into the Oort cloud, that vast spherical reservoir of comets surrounding the solar system. A distance is up to 100,000 astronomical units. Something, perhaps the gravitational influence of a passing star or a giant molecular cloud, perturbed Lemmon's orbit, sending it falling back toward the sun on the journey we're now observing. Its composition reflects primordial solar system chemistry, the isotope ratios and molecular abundances present in our local region of the galaxy 4.5 billion years ago. 3I Atlas formed somewhere else, around a different star, in conditions that might have been similar or radically different. The temperature and pressure in that protoplanetary disk, the abundance of heavy elements, the radiation environment, the timing of planet formation, all these factors influence comet composition and structure. By comparing interstellar comets to solar system comets, we're essentially comparing samples from different stellar nurseries, looking for commonalities that reveal universal processes and differences that highlight local variations. Lemmon serves as a real-time reminder of how fragile comets are. Every comet is a gamble against disintegration. Most survive their perihelion passage, lose some mass to sublimation, retreat back to the outer solar system or beyond, and remain intact. Some fragment dramatically, providing spectacular shows as multiple nuclei and expanding dust clouds brighten and fade. A few vanish completely, destroyed so thoroughly that tracking them afterward becomes impossible. Watching Lemmon during its peak visibility window isn't just about appreciating a beautiful celestial sight. It's about witnessing a survivor, an object that has endured billions of years in the deep freeze of the Oort cloud and is now running a gauntlet of solar heat and radiation that might or might not end in its destruction. The timing is fortuitous. While 3I Atlas hides behind the sun, Lemmon provides a substitute target, a different comet we can actually observe and study. If you haven't seen a comet with your own eyes, if you've only encountered them as images on screens or diagrams in textbooks, now is your chance. Go outside before dawn, find a dark location, let your eyes adapt for 10 or 15 minutes, and scan the eastern sky in Cancer. That fuzzy patch of light, if you find it, contains ice that formed before Earth existed. Organic molecules that predate life, silicate dust older than our planet. You're seeing a messenger from the beginning of the solar system, and in 2 weeks it will fade from view, its brief moment of visibility over, its destiny whether survival or disintegration still unwritten. Watch the skies now while Atlas hides. Part 7. The Swan and the Context. Comets tend to arrive in bunches, or at least that's how it seems to observers tracking these icy visitors. The reality is more prosaic. At any given time, numerous comets orbit the sun at various distances, most too faint to observe without large telescopes, a few bright enough to attract amateur attention, and very rarely one spectacular enough to become visible to the naked eye and enter public consciousness. The clusters we perceive result from observational bias and the statistical nature of comet discoveries, but they still create periods where comet watchers have multiple targets to choose from. 2025 is shaping up as one of those periods. Alongside Lemmon and the vanished 3I Atlas, another comet designated C/2025, R2 Swan has entered the catalog. Swan refers to the solar wind anisotropies instrument aboard the SOHO spacecraft, which observes the sky in ultraviolet wavelengths sensitive to hydrogen emission. Comets produce enormous hydrogen clouds, neutral hydrogen atoms created when water molecules break apart under solar ultraviolet radiation. These clouds are invisible to optical telescopes but glow brightly in specific UV wavelengths, and SWAN can detect them at vast distances, sometimes spotting comets months before they become visible to ground-based observers. C/2025 R2 SWAN was discovered through its hydrogen corona, that immense invisible cloud surrounding the visible coma. Follow-up optical observations confirmed the discovery and allowed trajectory calculations. The comet is following an elongated elliptical orbit that will bring it to perihelion in early 2026, well after Lemmon's close approach, but soon enough to maintain interest among comet observers preparing their equipment and observation plans. Early brightness estimates for SWAN suggest it might reach magnitude 6 or 7 at perihelion, making it a binocular object but probably not naked eye visible, except under exceptional circumstances. The predicted brightness depends on assumptions about nucleus size and activity level, both of which remain uncertain. Some comets discovered by SWAN have exceeded expectations, brightening significantly as they approach the Sun. Others have disappointed, remaining faint and diffuse despite hopeful predictions. The only way to know is to watch and wait. One intriguing possibility associated with new comets involves meteor showers. When a comet approaches the Sun, it sheds dust that spreads along its orbital path, creating a stream of particles. If Earth's orbit intersects this dust stream, the particles slam into our atmosphere at high velocity, typically 30 to 70 kilometers per second, and vaporize in bright streaks we call meteors or shooting stars. Most meteor showers we observe annually, like the Perseids in August or the Geminids in December, result from Earth passing through well-established dust trails left by comets that have made multiple perihelion passages, depositing dust over centuries or millennia. New comets, making their first passage through the inner solar system, can produce unpredictable meteor activity. The dust distribution along the orbit hasn't been smoothed out by repeated passages and planetary perturbations. Fresh outbursts might create dense clumps of particles. If Earth happens to pass through one of these clumps, meteor rates could spike dramatically, creating a meteor storm with hundreds or thousands of visible meteors per hour. These events are rare and difficult to predict because they depend on the exact spatial distribution of dust, which we can't measure directly. SWAN's orbit will be calculated precisely in the coming months, and astronomers will determine whether any potential Earth dust stream intersections might occur. Even a low probability possibility of a meteor shower gets comet and meteor enthusiasts excited. Observing a meteor storm is a bucket list experience, a celestial fireworks display that happens perhaps once or twice per generation. The meteors radiate from a point in the sky called the radiant converging perspective lines created by parallel particle trajectories entering the atmosphere. During a storm, the entire sky appears to rain meteors, streaks of light appearing in all directions, overwhelming the senses in a way that photographs can never fully capture. But for every comet that brightens and performs as hoped, several others fizzle. The history of comet astronomy is littered with predictions that failed, with objects expected to become great comets that instead remained faint and unremarkable. Comet Kohoutek in 1973 was predicted to become one of the brightest comets of the century that barely reached naked eye visibility, disappointing millions who had been promised a spectacular show. Comet unison in 2013 was supposed to survive perihelion and brighten dramatically, but instead disintegrated. These failures teach humility and remind us how much we still don't understand about comet physics. The comparison between SWAN and Lemmon's brightness curves will eventually provide useful scientific data. Two comets observed simultaneously under similar solar conditions allow direct comparison of activity levels in sublimation physics. Differences in brightness at comparable distances from the Sun indicate differences in nucleus size, composition, or surface properties. If one comet is water-dominated and the other carbon monoxide-dominated, their activity profiles will diverge in characteristic ways. If one fragments and the other doesn't, we gain clues about structural differences that determine fragmentation susceptibility. Using SWAN and Lemmon as foils creates narrative tension. Many comets fail, so will 3I Atlas fail too? Is there something about the current solar environment that makes comet survival less likely? The October 2025 coronal hole event could have been a one-time fluke, or it could signal a period of enhanced solar activity that threatens any comet passing through the inner solar system. The Sun's 11-year activity cycle is approaching solar maximum, the period when sunspots and coronal mass ejections become frequent, when solar wind speeds and magnetic field strengths increase. Comets approaching perihelion during solar maximum face harsher conditions than those arriving during solar minimum. Comet fragmentation history provides sobering statistics. Comet Shoemaker, Levy 9's tidal disruption by Jupiter in 1992, followed by the spectacular impacts in 1994, demonstrated how thoroughly a comet can be destroyed by gravitational and tidal forces. Comet 73, P. Schwarzmann-Wachmann, 3 fragmented during its 1995 apparition, splitting into multiple pieces that separated over subsequent years. By its 2011 return, the comet had broken into more than 60 identified fragments. A debris field spread along several thousand kilometers of orbit. Some fragments remained active, producing small Comet. Others appeared dormant, their volatiles depleted or sealed beneath inactive crusts. These fragmentation events matter for predicting space hazards. A single large comet nucleus poses minimal risk to Earth because the probability of the few kilometer-wide nucleus hitting our planet is vanishingly small. But a fragmenting comet creates dozens or hundreds of pieces, each capable of atmospheric entry, and while the individual pieces are smaller and less destructive than the original nucleus, the probability that one of them intersects Earth's path increases. Most comet fragments burn up harmlessly in the atmosphere or miss Earth entirely. But the risk calculation changes when you're dealing with distributed debris rather than a single object. Foreshadowing the 2060 comet event, predicted to be the brightest comet apparition of the century, puts current observations in perspective. Comets are the solar system's chaotic clock, appearing unpredictably, brightening erratically, fragmenting without warning. They mark time in human consciousness differently than the regular motions of planets and stars. A generation remembers Halley's Comet in 1986, a disappointing view for most but culturally significant. The generation before remembers Comet Hale-Bopp in 1997, visible to the naked eye for months, bright enough to see from city centers. The current generation may remember Lemmon or Swan or 3i Atlas, assuming any of them survive and brighten sufficiently. Are we in a cluster period of unusual comet appearances? Statistical analysis of comet discovery rates over decades shows fluctuations that might represent real clustering, or might simply reflect improvements in detection technology. More telescopes scanning more sky at greater sensitivities naturally find more comets. The Atlas survey that discovered 3i Atlas exists specifically to find near-Earth objects, and finds comets as a bonus. The Catalina Sky Survey, Mount Lemmon Observatory, Pan-STARRS in Hawaii, all these automated systems constantly watch for anything that moves, and comets move, so they get found. But there's a tantalizing hint in the data that the Oort cloud, that distant reservoir of comets, might experience perturbations that send showers of comets falling toward the inner solar system. Passing stars, gravitational interactions with giant molecular clouds in the galaxy, even the vertical oscillation of the solar system through the galactic plane as it orbits the Milky Way center, all these could shake comets loose. If real, these comet showers would occur on timescales of millions of years, far too long for human observation to detect directly. But buried in the geological record, evidence of impact clustering might reveal these ancient storms of comets that battered the inner solar system during the dinosaurs' reign, or even earlier in Earth's history. Comets function as the solar system's chaotic clock precisely because they don't follow regular predictable paths like planets. Most planets orbit in nearly circular paths, their positions calculable centuries in advance with high precision. Comets arrive from the outer darkness on highly elliptical orbits, their return times, if they return at all, spanning decades, centuries, or millennia. Some are new visitors, first-time fallers from the Oort cloud, others are short-period comets trapped by Jupiter's gravity into orbits that bring them back every few years. They remind us that the solar system is not a clockwork mechanism of perfect orbits, but a dynamic, chaotic environment, where gravitational interactions constantly shuffle trajectories and new players enter the stage without announcement. Part 8. The Unbreakable Signal. While astronomers scan the skies for comets and track solar wind, another kind of cosmic race unfolds in laboratories and ground stations here on Earth. In 2025, China announced completion of the world's longest quantum communication link, the 12,900-kilometer network connecting Beijing to distant ground stations through satellite relays, and claimed the system provides effectively unhackable data transmission. The announcement represents a milestone in the quantum information revolution, and if the system works as advertised, it changes the landscape of global communications and cybersecurity in ways that extend far beyond immediate military or commercial applications. Quantum key distribution, the underlying technology, exploits fundamental properties of quantum mechanics to detect eavesdropping. The basic principle is elegant and strange in equal measure. Information gets encoded in the quantum states of photons, single particles of light transmitted through optical fibers or through space between satellites and ground stations. The quantum no-cloning theorem guarantees that these states cannot be copied perfectly. Any attempt to measure or intercept the photons necessarily disturbs them in detectable ways. This means two parties sharing a quantum communication channel can generate encryption keys and know with certainty whether anyone tried to intercept those keys during transmission. The process begins with entangled photons, pairs of particles created simultaneously, and sharing a quantum connection such that measuring properties of one photon instantly affects the other, regardless of the distance separating them. This phenomenon, which Einstein famously called spooky action at a distance, has been verified in countless experiments and forms the basis for several proposed quantum technologies, including quantum computing and quantum teleportation. For quantum key distribution, entangled photons allow two parties to establish shared random numbers that can be used as encryption keys. Hardware implementation requires extraordinary precision. Photons must be generated, entangled, transmitted, and detected with minimal loss and maximal fidelity. Optical systems must align satellite transceivers with ground stations across hundreds or thousands of kilometers while compensating for atmospheric turbulence, satellite motion, and Earth's rotation. Single photon detectors must register individual particles arriving at rates of thousands or millions per second, distinguishing real signals from background noise and detected dark counts. Error correction protocols must account for inevitable imperfections while still guaranteeing security. China's system uses the Messiah satellite, launched in 2016 and named after an ancient Chinese philosopher. The satellite orbits at roughly 500 kilometers altitude, passing over ground stations in a sun-synchronous orbit that provides regular communication windows. During each pass, lasting several minutes, the satellite distributes entangled photons to pairs of ground stations, allowing them to establish shared encryption keys. These keys then secure conventional data transmission using standard encryption algorithms, with the quantum channel guaranteeing that the keys themselves weren't compromised. The recent expansion to 12,900 kilometers represents a significant engineering achievement. Earlier demonstrations covered shorter distances or relied on trusted relay stations that theoretically could be compromised. The new system chains quantum links across multiple satellite passes and ground stations, creating end-to-end security across continental scales. According to Chinese researchers, the network already serves government and financial institutions, protecting communications against both current and future decryption threats. That last point matters crucially. Current encryption systems, the ones protecting everything from bank transactions to classified government communications, rely on mathematical problems that are computationally difficult to solve with classical computers. Factoring large numbers, computing discrete logarithms, these tasks require so much computational time that breaking encryption becomes impractical even with the fastest supercomputers available. But quantum computers, if built at sufficient scale, could solve these problems efficiently, rendering current encryption obsolete. Data encrypted today and captured by adversaries could be decrypted years or decades in the future, once quantum computers mature. Quantum key distribution offers protection against this harvest now, decrypt later threat because the security doesn't rely on computational difficulty, but on fundamental physics. Western nations, particularly the United States and European countries, view China's progress in quantum communications with concern. The MIT Technology Review Quantum Index in 2025 ranks China ahead in several quantum technology metrics, including quantum communications and quantum sensing. American research programs are working to catch up with the Department of Energy funding quantum network testbeds and DARPA exploring space-based quantum communication architectures. But China's early lead and substantial government investment have created a quantum gap that worries defense planners and technology strategists. The policy implications extend beyond simple technological competition. If quantum communication networks become the backbone of future secure communications, Nations without access to the technology face potential information disadvantage. International agreements governing quantum technology development remain nascent. Questions about export controls, technology transfer, and standardization remain unresolved. Some researchers advocate for open collaboration and shared development of quantum networks as global infrastructure, similar to how the Internet developed as an international resource. Others push for competitive advantage and restricted access, viewing quantum superiority as a strategic asset too valuable to share. Could space-based quantum networks become the backbone of the future Internet? The vision involves constellations of quantum satellites providing global coverage, ground stations in every major city, and quantum repeaters extending range beyond direct line-of-sight limits. Data would travel encrypted by quantum keys that refresh continuously, immune to interception, resistant even to future technologies we haven't yet imagined. The system would integrate with existing fiber optic networks, providing a hybrid classical quantum infrastructure where quantum channels distribute keys and classical channels carry bulk data. Conspiracies naturally emerge around technologies this advanced and this secret. Quantum key distribution systems require extensive testing and calibration, processes that generate data about photon transmission statistics, detector efficiency, and error rates. Most of this data remains classified or proprietary. Chinese publications describe the system's capabilities in general terms, but omit engineering details that would allow independent verification or replication. Western intelligence agencies undoubtedly monitor the program closely, using signals, intelligence, and other means to assess its actual capabilities versus public claims. This opacity feeds speculation about whether the system works as advertised or whether vulnerabilities exist that aren't being disclosed. Some worry about state surveillance potentials. A government controlling a nationwide quantum communication network has unprecedented ability to monitor who communicates with whom, even if the content remains encrypted. Metadata, the information about communication patterns rather than communication content, often reveals as much as the messages themselves. Traffic analysis can identify social networks, track movements, predict behavior. A quantum network that logs every connection, every photon transmission, every key generation event, creates a surveillance infrastructure of staggering scope. The tie-in to the Three-Eye Atlas narrative rests on an interesting parallel. Just as comets carry messages from other star systems, encoded not in language but in chemistry and isotope ratios, humans now build systems to carry unbreakable encoded messages across our own planet. Both represent information that survives hostile environments, comet chemistry surviving interstellar space and solar heat, quantum keys surviving active adversaries trying to intercept them. Both push the boundaries of what's possible. Comets as natural information carriers shaped by billions of years of physics, quantum networks as artificial information carriers shaped by decades of engineering. Unknowns remain numerous. Current quantum key distribution rates, typically measured in kilobits per second, lag far behind classical communication speeds measured in gigabits or terabits per second. Scaling quantum networks to handle internet-level traffic requires either dramatic improvements in photon transmission, and detection efficiency, or fundamentally new approaches to quantum networking. Decoherence, the loss of quantum properties due to environmental interactions, places fundamental limits on how long quantum states can be maintained and how far they can be transmitted. Satellites help extend range by operating in the vacuum of space above most of the atmosphere. But atmospheric turbulence at ground stations still degrades performance. Endpoint security presents another challenge. Quantum key distribution guarantees secure key transmission, but the keys must ultimately be used by classical computers to encrypt and decrypt data. If those computers are compromised through malware, physical access, or side-channel attacks that monitor electromagnetic emissions or power consumption, the unbreakable quantum keys become irrelevant. Security is only as strong as the weakest link, and in any real system, weak links proliferate. The quantum space race narrative captures something true about human nature and technological development. We compete even in understanding and harnessing the fundamental laws of physics. Quantum mechanics, arguably the most successful physical theory ever developed in terms of predictive accuracy and technological impact, becomes a weapon in geopolitical competition. The same quantum principles that explain atomic structure and chemical bonds now secure communications and promise revolutionary computing power. Nations invest billions in quantum research, not out of pure scientific curiosity, but because quantum technology might determine military balance and economic leadership in the coming decades. Whether this competition drives innovation faster than collaboration would, whether the benefits of quantum networks will be shared globally or concentrated in a few technologically advanced nations, these questions remain unanswered as the race accelerates. Part 9. The circular economy inside you. Science occasionally produces discoveries so unexpected, so contrary to intuition, that they force us to reconsider fundamental assumptions about what's possible. The announcement that synthetic biologists have engineered yeast to convert human urine into bone mineral hydroxyapatite represents one of those discoveries. The potential applications range from medical to ecological, and the deeper implications touch on questions of waste, value, and the surprising ways that biological systems can be reprogrammed to transform one substance into another. Urea, the primary nitrogen-containing component of urine, serves as waste product in mammalian metabolism. When proteins break down in the body, amino acids get metabolized, and the nitrogen they contain must be excreted. Aquatic animals excrete ammonia directly, a simple and energetically cheap solution when you live in water that dilutes and carries away the toxic compound. Land animals face a challenge. Ammonia is too toxic to accumulate, but water conservation matters, so terrestrial animals evolved more complex solutions. Birds and reptiles produce uric acid, a relatively insoluble compound that precipitates out and can be excreted as a paste, minimizing water loss. Mammals produce urea, soluble enough to transport in water but less toxic than ammonia, excreted in liquid urine that represents a compromise between water conservation and waste removal. Humans produce roughly 1 to 2 liters of urine daily, depending on fluid intake and metabolic rate, containing about 20 to 30 grams of urea. That's roughly 10 kilograms of urea per person per year, multiplied by 8 billion people globally, giving roughly 80 million metric tons of urea excreted annually. Currently, this urea ends up in sewage systems, or it's broken down by bacteria or released into the environment. The new synthetic biology approach asks whether this waste stream might be converted into something valuable. Hydroxyapatite is the mineral component of bone and teeth, a calcium phosphate compound with the formula Ca10PO4OH2. It provides the hardness and structural integrity that allows bones to support body weight and protect organs. Natural bone is a composite material, hydroxyapatite crystals embedded in a collagen protein matrix, combining the hardness of mineral with the flexibility and toughness of organic fibers. Medical applications require pure hydroxyapatite for bone grafts, dental implants, and reconstructive surgery. Currently, hydroxyapatite gets synthesized through chemical processes or harvested from animal bones, both approaches having limitations in purity, crystal structure, and production cost. The engineered yeast approach works through metabolic pathway engineering. Research has identified the series of enzymatic reactions needed to convert urea into the chemical precursors of hydroxyapatite, then inserted genes encoding those enzymes into yeast cells. The yeast, normal Saccharomyces cerevisiae, commonly used in brewing and baking, now contain synthetic metabolic pathways that don't exist in nature. When fed urine as a nitrogen source and provided with calcium and phosphate ions, the yeast cells produce hydroxyapatite crystals that precipitate out and can be harvested. The mechanism involves multiple steps. Urease enzyme breaks urea into ammonia and carbon dioxide. The ammonia gets incorporated into amino acid synthesis pathways, while the carbon dioxide and additional calcium and phosphate ions undergo mineralization reactions that form hydroxyapatite. The precise crystallography of the product, the size and shape and purity of the hydroxyapatite crystals, depends on reaction conditions including pH, temperature, ion concentrations, and the genetic programming of the yeast pathways. Early results show promise, producing hydroxyapatite with properties similar to bone mineral, but significant optimization remains before the process becomes practical for medical applications. Current efficiency and yield rates limit immediate applications. The yeast produces hydroxyapatite at concentrations too low for commercial viability, requiring large bioreactor volumes to generate meaningful quantities. Purification challenges arise because the hydroxyapatite must be separated from yeast cells, growth medium components, and metabolic byproducts. Purity matters critically for medical use. Foreign proteins or bacterial endotoxins in implanted hydroxyapatite could trigger immune responses or infections. Achieving medical-grade purity from a biological production system requires rigorous quality control and purification protocols. Nevertheless, the potential is transformative. Bone fractures affect millions of people annually, and while most heal naturally, complex fractures or bone loss due to disease or trauma often require grafts or synthetic materials to support healing. Current bone graft materials include autografts harvested from the patient's own body, allografts from cadavers, and synthetic ceramics. Each option has drawbacks. Autografts require additional surgery to harvest the graft tissue. Allografts carry small risks of disease transmission and immune rejection. Synthetic ceramics sometimes fail to integrate well with natural bone. Hydroxyapatite produced biologically from waste materials could provide an abundant, cost-effective alternative if production and purification challenges get solved. Dental implants represent another major market. Hydroxyapatite coatings on titanium implants improve osseointegration, the bonding between implant and jawbone. Current coatings use hydroxyapatite produced through high-temperature chemical sintering, an energy-intensive process. Biological production at room temperature in aqueous solution would reduce energy costs and carbon footprint, while potentially creating more bone-like crystal structures that integrate better with living tissue. Ecological benefits extend beyond the direct use of the material. Urea in wastewater contributes to eutrophication when released into rivers and coastal waters. Excess nitrogen stimulates algal growth, leading to blooms that deplete oxygen and create dead zones. Capturing urea and converting it to solid mineral removes nitrogen from the waste stream, reducing environmental impact. The process represents waste valorization, the principle of treating waste as a resource rather than a disposal problem. Controversies naturally emerge around using human waste in medical materials. Cultural taboos about urine and feces run deep, even though intellectually we understand that purified compounds have no memory of their origin. The calcium atoms in hydroxyapatite produced from urine are identical to calcium atoms from any other source. The material, once purified, carries no trace of waste beyond the historical fact of its production pathway. Yet psychological resistance remains. Would patients accept bone grafts or dental implants produced from urine? Would regulatory agencies approve such materials for human use? These questions touch on cultural values and risk perception more than technical feasibility. Astronaut applications provide perhaps the most compelling use case. Mars colonists or long-duration space missions face resource constraints that make every recycling opportunity valuable. Crew members will produce urine daily regardless, and that urine contains nitrogen and other elements that must be processed and either recycled or disposed of. Converting urine into usable hydroxyapatite for medical purposes or structural materials kills two birds with one stone, managing waste and producing useful products. The closed-loop life support systems needed for space exploration push designers toward maximal recycling and minimal waste. Your waste could literally save your life if a bone fracture on Mars requires a graft, and the only available hydroxyapatite was produced from crew urine. Big pharma resistance to circular biotech adoption represents a predicted, rather than demonstrated, conspiracy. Pharmaceutical and medical device companies profit from current production methods and supply chains. Disruptive technologies that threaten existing business models face resistance regardless of their technical merit. Whether this resistance materializes for urine-derived hydroxyapatite depends on factors including production costs, scalability, regulatory pathways, and intellectual property landscapes. If the technology can be patented and controlled by established players, adoption becomes more likely. If it threatens to commoditize a high-margin product, resistance becomes more likely. The deeper takeaway transcends any specific application. Nature wastes nothing. Nutrients cycle through ecosystems. One organism's waste becomes another's food. Energy flows and elements circulate. Humans evolved in cultures where waste disposal was simpler because population densities were low and natural processes degraded and recycled most waste products. Industrialization and urbanization broke these cycles, creating waste streams that overwhelm natural recycling capacity. Synthetic biology offers tools to rebuild those cycles artificially, engineering organisms to fill ecological niches that don't exist naturally but that serve human needs. Converting urine to bone mineral is just one example. The same principles apply to converting carbon dioxide to fuel, plastic waste to biodegradable polymers, agricultural runoff to valuable chemicals. We're learning to close loops that our technological development opened, catching up to the circular economy that nature perfected over billions of years. Part 10. The yawn that crosses species. Animal behavior provides endless fascination because it reflects cognitive and emotional states we recognize from our own experience, yet manifests in creatures whose minds remain alien to us. Contagious yawning, the phenomenon where witnessing someone yawn triggers the irresistible urge to yawn yourself, seemed until recently to be limited to humans and a few other highly social mammals like chimpanzees and dogs. The publication of a study demonstrating contagious yawning in zebrafish challenges that assumption and raises puzzling questions about the evolutionary origins and neural mechanisms underlying this behavior. Zebrafish, small freshwater fish native to South Asian rivers and popular in both scientific research and home aquariums, have become model organisms for studying vertebrate development and behavior. Their embryos are transparent, allowing researchers to watch organs form in real time under microscopes. Their genetics are well characterized, with tools available for manipulating genes and observing the results. They're small, cheap to maintain, and produce hundreds of offspring, making them ideal for large-scale experiments. But nobody expected them to yawn contagiously. The experimental setup involved placing zebrafish in adjacent tanks, where they could see each other through transparent walls. Researchers induced yawning in one fish through oxygen deprivation, a known trigger for yawning in many species. Cameras recorded the behavior of both the yawning fish and the observers. Analysis revealed that observer fish yawned significantly more frequently after witnessing a neighboring fish yawn, with timing correlations suggesting genuine contagion, rather than coincidental yawning triggered by shared environmental conditions. Why is this shocking? Contagious yawning was thought to require mirror neurons or similar neural circuits that allow an animal to mentally simulate the actions and states of others. These circuits, concentrated in primate brains and suspected in certain social mammals, provide the neural basis for empathy, imitation learning, and theory of mind. Fish brains lack the cortical structures where mammalian mirror neurons reside. Their neural organization is fundamentally different, simpler in some respects, though certainly not simple overall. The presence of contagious yawning in zebrafish suggests either that the behavior doesn't require the sophisticated neural machinery we assumed, or that convergent evolution produced similar circuits in fish through entirely different anatomical pathways. Neural circuits underlying yawning in any species remain incompletely understood. The act itself involves coordinated contraction of muscles in the jaw, face, throat, and respiratory system, producing the characteristic gaping mouth, and deep inhalation followed by slower exhalation. The behavior appears involuntary once triggered, resistant to conscious suppression
despite social contexts where yawning might be inappropriate. Multiple triggers exist, including fatigue, boredom, low oxygen, and the sight of others yawning. The diverse triggers suggest multiple neural pathways converging on a common motor output. In humans, contagious yawning increases during childhood development, peaks in young adulthood, and shows correlation with empathy measures. People scoring high on empathy questionnaires yawn more readily when watching others yawn. Individuals with autism spectrum disorders, who often struggle with social cognition and empathy, show reduced contagious yawning. These correlations support the hypothesis that contagious yawning relies on neural systems involved in social cognition and emotional resonance. Finding the same behavior in zebrafish, creatures we don't typically credit with empathy or sophisticated social cognition, challenges this neat story. The evolutionary mystery deepens when considering the taxonomic distribution. Contagious yawning appears in humans, chimpanzees, bonobos, dogs, and now zebrafish. It's absent or hasn't been demonstrated in many species tested, including cats, horses, and most birds. The scattered distribution across the animal kingdom suggests either multiple independent origins of the behavior or an ancient origin with subsequent loss in many lineages. Neither explanation is entirely satisfying. Convergent evolution of something as specific as contagious yawning in mammals and fish seems unlikely unless the behavior serves an important function we're missing. Ancient origin requires explaining why so many species lost it. Hypotheses about function vary widely. One proposal suggests contagious yawning serves group coordination, synchronizing states of arousal or attention across social groups. If one individual detects a change in environmental conditions that triggers yawning, perhaps signaling a transition from alertness to rest, spreading that signal through the group helps coordinate collective behavior. Fish schools certainly require coordination. They move as units, turning simultaneously, maintaining precise spacing, responding to threats with synchronized evasive maneuvers. Could contagious yawning be part of the behavioral toolkit that enables this coordination? Another hypothesis focuses on stress relief and social bonding. Yawning might serve to regulate stress hormones or reset neural states under social stress conditions. Seeing others yawn and yawning in response could create a feedback loop that helps groups collectively manage tension. Zebrafish are social animals that school in nature, and social dynamics involve dominance hierarchies, mate competition, and predator vigilance. Perhaps contagious yawning plays a role in maintaining group cohesion under stress. The controversy centers on whether the behavior observed in zebrafish genuinely qualifies as yawning, rather than some other jaw movement or gill action being misclassified. Fish don't breathe air under normal circumstances, so the respiratory component of mammalian yawning has no direct analog. The gaping mouth movement observed in zebrafish could serve different physiological functions related to gill ventilation or feeding. Critics argue that without clear evidence, the fish behavior shares the same neural triggers and physiological consequences as mammalian yawning. Calling it contagious yawning anthropomorphizes a superficially similar but functionally distinct behavior. Proponents counter that the behavior shares key features with mammalian yawning, including involuntary nature, stereotyped motor pattern, triggering by hypoxia, and now demonstrated social contagion. The neural pathways may differ between fish and mammals, separated by hundreds of millions of years of evolution. But if the behavior serves similar functions and responds to similar triggers, the term yawning applies legitimately. Biology is full of convergent evolution, where different structures serve similar functions. Bird wings and bat wings are anatomically distinct, but functionally equivalent. Perhaps fish yawning and mammalian yawning represent convergent solutions to similar behavioral or physiological challenges. Speculation extends into deeper biological territory. Could yawn contagion represent a universal signal, an ancient communication channel that predates more sophisticated social cognition? Perhaps the basic neural circuitry that makes yawning contagious evolved early in vertebrate history, preserved across hundreds of millions of years because it serves fundamental coordination functions in social species. This would require the behavior to provide significant fitness benefits, to improve survival or reproduction enough that natural selection maintains it despite the costs of the neural machinery required. The fringe possibility, rarely voiced in academic contexts but whispered in conference hallways, asks whether synchronization phenomena might extend beyond individual species, perhaps even across kingdoms of life. Yawn contagion, as currently understood, operates through sensory perception. Seeing or hearing someone yawn triggers neural pathways that produce yawning. that broader synchronization in nature occurs through mechanisms we're only beginning to understand. Heart cells beating in culture synchronize their rhythms through electrical and chemical signaling. Fireflies in Southeast Asian mangroves synchronize their flashing across hundreds of individuals. Could there be deep biological principles of synchrony and resonance that manifest in yawn contagion among other phenomena? The narrative tie-in to cosmic themes works through the concept of resonance and synchronization across scales. Fish schools move as coordinated units, responding to each other's movements through lateral line sensors that detect water pressure changes. Flocks of birds turn simultaneously, each individual following simple rules about spacing and alignment that produce complex emergent patterns. At larger scales, planets orbit in resonances, gravitational interactions locking their periods into integer ratios. Jupiter's moons, Europa, Ganymede, and Io, orbit in a 4 to 2 to 1 resonance, each orbital configuration repeating. At cosmic scales, galaxy clusters move under mutual gravitational influence, their dynamics coupled across millions of light years. Synchronization appears as a fundamental principle, organizing systems from molecular to cosmic scales. Oscillators, whether neurons firing, hearts beating, pendulums swinging, or planets orbiting, tend to phase lock when coupled, their rhythms entraining to common frequencies. The mathematics of coupled oscillators reveals surprising commonalities across wildly different physical systems. Perhaps yawn contagion represents a biological instantiation of these universal synchronization principles, a social oscillator that couples through observation and triggers phase-locked responses. Human brains and stars may have more in common than we think, if we shift perspective from specific mechanisms to abstract principles. Both are complex dynamical systems with internal structure, emergent properties, and couplings to external environments. Both process information, though in radically different ways and at vastly different scales. Brains process sensory inputs and generate behavioral outputs through electrochemical signaling across neural networks. Stars process gravitational inputs and generate radiation outputs through nuclear fusion regulated by hydrostatic and thermal equilibrium. The analogy breaks down quickly if pushed too hard, but it gestures toward deep questions about complexity, information, and organization in the universe. The zebrafish study at its core reminds us how little we truly understand about animal minds and behaviors. Every assumption, every supposedly established fact about what animals can and cannot do remains provisional, subject to revision when new evidence appears. We thought contagious yawning required empathy and mirror neurons. Fish apparently didn't receive that message. What other behaviors we consider uniquely human or uniquely mammalian might have deeper roots or broader distribution than we realize? Tool use appears in birds and octopuses. Culture, defined as learned behaviors transmitted socially across generations, exists in whales and crows. Metacognition, thinking about thinking, shows hints in rats and dolphins. The more we look, the more we find that the boundaries we draw between humans and other animals, between complex minds and simple minds, blur under scrutiny. Part 11. The Stone That Will Skim Earth's Atmosphere. April 13th, 2029 will be a date humanity remembers, assuming we're still here to remember things. On that day, asteroid 99,942 Apophis, named for the ancient Egyptian demon of chaos and darkness, will pass Earth at a distance of 31,000 kilometers. To put that in perspective, geostationary satellites orbit at roughly 35,000 kilometers. Apophis will pass inside the ring of satellites that provide weather forecasting, communications, and GPS navigation. It will be visible to the naked eye, a point of light moving rapidly against the stars, the first time in recorded history that an asteroid of this size has come so close to Earth that casual observers can watch it pass. Current orbital calculations show no impact risk. The close approach is certain, the geometry well understood, that the trajectory will carry Apophis safely past our planet without collision. This certainty represents decades of careful observation and orbital refinement. When Apophis was discovered in 2004, initial trajectory calculations couldn't rule out a small but non-zero probability of impact during its 2029 pass. The announcement triggered brief public alarm and intense scientific interest. Subsequent observations as the asteroid appeared in different parts of its orbit refined the calculations, shrinking the uncertainty ellipse the region where the asteroid might be at any given time, until the 2029 impact possibility was ruled out completely. But the story doesn't end in 2029. The close pass will alter Apophis's orbit through gravitational interaction with Earth. When an asteroid passes near a planet, tidal forces and gravitational acceleration change its trajectory, sometimes dramatically. The degree of change depends on how close the approach is and the relative velocities. Apophis will experience significant orbital deflection, changing its period around the Sun and shifting its future Earth-crossing potential. Predictions for subsequent close approaches in 2036 and 2068 involve larger uncertainties, because those future positions depend on the exact details of the 2029 encounter, details we can't measure precisely until the encounter happens. The distance, closer than geostationary orbit, makes this an unprecedented scientific opportunity. Telescopes will track Apophis continuously as it approaches, measuring its rotation state, mapping its surface features, determining its composition through spectroscopy, measuring its size and shape with radar. The asteroid is roughly 370 meters in diameter, large enough to cause regional devastation if it ever did impact, but small enough that detecting surface details from Earth-based observations remains challenging. The close pass brings it within range of techniques normally reserved for near-Earth objects during even closer approaches. Radar astronomy will play a crucial role. Radio telescopes like the Goldstone antenna in California and the Arecibo replacement facility, assuming it's operational by then, can bounce radio waves off asteroid surfaces and analyze the echoes. Radar provides precise distance measurements accurate to meters, rotation period measurements accurate to seconds, and surface roughness information that optical telescopes can't match. Delay Doppler radar imaging creates two-dimensional pictures where one axis represents distance, the time delay of the echo, and the other represents velocity, the Doppler shift of the echo. These radar images reveal shape, rotation, and surface features, sometimes detecting boulders, craters, and ridges only meters across. Rotation studies matter because asteroids spin, and their spin states carry information about their history. Apophis rotates with a period of approximately 30 hours, determined from light curves showing how its brightness varies as different faces reflect sunlight toward Earth. This rotation rate is stable now, but the 2029 Earth encounter will change it. Tidal forces acting on the asteroid as it passes Earth will torque its rotation, potentially speeding it up or slowing it down depending on the geometry. Measuring the rotation change provides data about the asteroid's internal structure, whether it's a solid monolith or a rubble pile of smaller pieces held together loosely by gravity. The Yarkovsky effect adds another layer of complexity. Asteroids absorb sunlight, warming their surfaces, then re-radiate that energy as infrared heat. The thermal radiation carries momentum, creating a tiny rocket effect that pushes the asteroid. For a rotating asteroid, the afternoon side is warmer than the morning side, and the asymmetric thermal emission creates a small but persistent force that either speeds the asteroid up or slows it down in its orbit, depending on whether it rotates prograde or retrograde. Over millions of years, the Yarkovsky effect can change orbit significantly, shifting asteroids from the main belt into Earth-crossing trajectories. For Apophis, the Yarkovsky effect must be measured precisely to predict its long-term orbital evolution. The effect is tiny, creating orbital changes of only meters per year, but those meters accumulate over decades into kilometers of position uncertainty. The 2029 close approach provides an opportunity to measure Yarkovsky acceleration by comparing the asteroid's actual position against predictions that don't include thermal effects. Any discrepancy indicates Yarkovsky influence and allows calibration of models used to predict future encounters. Public perception represents a challenge and opportunity. Apophis has appeared in news headlines repeatedly since its discovery, usually accompanied by alarming language about killer asteroids and cosmic threats. The actual risk is low to negligible for any encounter calculated so far, but risk communication is difficult. Explaining that there's a 1 in 45,000 chance of impact in 2068, the current estimate, means different things to different people. Statisticians understand it as negligible risk, far lower than countless risks we accept daily. But to someone unfamiliar with probability, 1 in 45,000 sounds concerning, like a real possibility rather than an essentially impossible event. proposals for Apophis missions have circulated in the planetary defense community. Sending a spacecraft to rendezvous with the asteroid during or after its 2029 Earth encounter would provide close-up data impossible to obtain from Earth. The mission could characterize the asteroid's composition, internal structure, and surface properties in detail. It could also serve as a demonstration of deflection technology, using techniques like kinetic impact or gravity tractor to slightly alter Apophis's orbit and prove that we possess the capability to protect Earth from future asteroid threats. NASA's DART mission, Double Asteroid Redirection Test, successfully impacted the asteroid Dimorphos in 2022, demonstrating kinetic deflection works as predicted. The impact changed Dimorphos's orbit around its larger companion Didymos, proving that humans can alter asteroid trajectories given sufficient warning time. An Apophis mission would build on DART's success, testing deflection techniques on a larger, potentially more scientifically interesting target. Conspiracy theories about NASA downplaying impact odds are predictable and unfounded, but psychologically understandable. Space agencies face a difficult balance between transparency and avoiding panic. Releasing every preliminary orbit calculation, with its associated uncertainties, creates alarm when the uncertainties are large, even though large uncertainties are normal for newly discovered objects with limited observational data. Waiting until calculations are refined before making announcements risks accusations of cover-up if someone discovers the object independently or leaks occur. NASA and other agencies have generally erred toward transparency, publishing orbit calculations and impact probabilities through the Century System and Torino scale. But transparency doesn't prevent conspiracy theories. It just shifts them from covering up impacts to covering up deflection failures or alien involvement. The narrative frame of the asteroid that will brush Earth's cheek captures the mixture of danger and wonder these close approaches inspire. Apophis won't hit us, but it will come close enough that we'll feel its presence, watch it pass, see the cosmic machinery that occasionally delivers mountain-sized rocks to Earth's vicinity. The close pass reminds us that space is not empty, that debris from solar system formation still orbits out there, that occasionally that debris crosses paths with Earth, and that while we've been fortunate so far, luck doesn't last forever. Preparation matters. Detection, tracking, characterization, and deflection capabilities represent humanity's insurance policy against the cosmic lottery that eventually delivers an impact. The event also serves as a global teachable moment. Planetary defense requires international cooperation. Asteroids don't respect borders, and a threat to one nation is a threat to all. The United Nations Committee on the Peaceful Uses of Outer Space coordinates international efforts to track near-Earth objects and develop response capabilities. The 2029 Apophis flyby will likely trigger renewed interest in planetary defense funding and policy, potentially accelerating development of detection networks and deflection technologies. Looking ahead to 2040's planetary parade provides context. The universe operates on schedules that ignore human timeframes. Asteroids arrive when orbital mechanics dictate. Planets align according to Kepler's laws. Comets fall from the Oort cloud following gravitational perturbations that started millennia ago. We mark these events on calendars, anticipating them, preparing for them, but they unfold according to physics, not human convenience. Apophis will pass in 2029 regardless of whether we're watching, whether we care, whether we're ready. The indifference of the cosmos to human concerns is both terrifying and liberating. Part 12. When Planets Dance. September 20th, 2040. Mark it on whatever calendar system survives the intervening years, because on that date the solar system will present a geometric arrangement rare enough to attract attention, and common enough that similar configurations recur with predictable frequency. 6 planets: Mercury, Venus, Mars, Jupiter, Saturn, and Uranus will occupy a relatively narrow band of sky as seen from Earth. Their longitudes, the angular positions along the ecliptic, separated by less than 90 degrees. The media will undoubtedly call this a planetary alignment or parade, though technically the planets won't line up in a straight line. They'll simply cluster in one region of the sky simultaneously visible from Earth's night side. The geometry works like this. Planets orbit the Sun in approximately the same plane, the ecliptic, defined by Earth's orbital plane. From our perspective, planets appear to move along a path across the sky that follows the zodiac constellations. Sometimes planets spread around the entire ecliptic, visible at different times as Earth rotates. Other times, their orbital positions cluster so multiple planets appear in the same region of sky simultaneously. These clustering events occur regularly but irregularly, the result of planets with different orbital periods occasionally lining up their positions. The rarity depends on how many planets we require to participate and how tightly we define alignment. Getting all 8 planets within a 90-degree band happens every few decades. Getting them within 30 degrees happens every few centuries. Getting them in an actual straight line, all planets at 0-degree separation as seen from the Sun, probably never happens within human timescales because orbital periods don't share exact integer ratios that would create perfect recurring alignments. The 2040 event will be particularly favorable for observation because the planetary cluster will include bright naked eye planets, Mercury, Venus, Mars, Jupiter, and Saturn, all easily visible without optical aid, plus Uranus, which requires binoculars or small telescopes. Neptune will be elsewhere in its orbit, not participating in the clustering. The planets will be visible in the evening sky after sunset, rising together in the east and arcing across the southern sky, depending on observer latitude, providing hours of viewing opportunity. Amateur astronomers will have a field day. Capturing all visible planets in one wide-angle photograph becomes possible during these events, creating images that showcase the architecture of the solar system. The different brightnesses and colors of planets provide visual interest. Venus appears brilliantly white, Mars distinctly orange-red, Jupiter yellowish-white, Saturn similar to Jupiter but slightly fainter, Uranus barely visible as a pale blue-green disk even in binoculars. Photographing them together creates a portrait of planetary diversity compressed into a single frame. Professional astronomers will seize opportunities beyond pretty pictures. Planetary alignments don't create any special gravitational effects despite persistent myths about tidal forces or seismic triggering, but they do provide occasions to make simultaneous measurements across multiple planets using the same instruments and techniques. Comparative planetology benefits from such opportunities. Measuring atmospheric properties of Venus, Jupiter, and Saturn during the same observation window controls for instrumental and observational variables, allowing more confident comparisons. The alignment might also provide opportunities to detect unusual objects. When planets cluster, the background star field in that region gets observed more intensity than usual. Faint asteroids, distant comets, or even undiscovered planets in the outer solar system might be spotted by observers scanning the region looking for planets. The hypothetical Planet 9, proposed to explain orbital clustering of distant trans-Neptunian objects, remains undiscovered despite searches. Its predicted location, if it exists, wanders slowly through the zodiac, and it might happen to be near the region of planetary clustering in 2040, making detection more likely simply because more telescopes will be pointed that way. Mythological and cultural contexts surround planetary alignments across human history. Ancient astronomers tracked planetary positions carefully, noting conjunctions and alignments, attributing significance to these events. Astrological traditions, which persist despite lack of scientific support, assign meaning to planetary configurations based on symbolism and perceived correlations. The scientific worldview rejects these associations as pattern-seeking, applied to random coincidence, but the human psychological response to celestial alignments remains strong. When planets gather in one part of the sky, it feels significant, even if we intellectually understand it's just orbital geometry. Some fringe communities will inevitably predict catastrophic consequences from the 2040 alignment. Planetary gravitational forces supposedly causing earthquakes or weather disasters represent recurring doomsday scenarios unsupported by physics. The gravitational influence of planets on Earth is negligible compared to the Moon and Sun. Even when planets align, their combined gravitational pull adds tiny perturbations to Earth's orbit that have no measurable effect on geological or atmospheric processes. But facts don't prevent prediction, and somewhere online, someone will claim the alignment will trigger disasters, and other people will believe them and prepare. And when the disasters don't materialize, the predictions will be quietly forgotten or rationalized away. Hidden scientific opportunities in alignments include mass distribution measurements in the solar system. Precise tracking of planetary positions allows tests of gravitational theories and refinement of planetary masses. Every planet affects every other planet gravitationally, creating perturbations in orbits that accumulate over time. By measuring where planets are and comparing to where Newtonian gravity predicts they should be, astronomers can detect anomalies that might indicate unknown masses elsewhere in the solar system, or, more speculatively, deviations from gravitational theory itself. The cultural dimension of alignments as global events matters in an increasingly connected world. Unlike eclipses, which are visible only from specific geographic locations, planetary configurations are visible globally, weather permitting. This creates shared experiences across cultures and continents. In 2040, people in Tokyo and New York and Sydney and Lagos will see the same planetary arrangement, creating a moment of cosmic commonality that transcends political and cultural divisions. The comparison to a planetary choir works metaphorically. Each planet moves at its own tempo, Mercury racing around the Sun every 88 days, Neptune creeping along, taking 165 years per orbit. These different periods create complex rhythms and patterns over time. When planets cluster, it's like a moment in a long cosmic symphony, where multiple instruments sound simultaneously, creating a chord before drifting apart again into individual melodies. The metaphor shouldn't be pushed too far because planets don't actually make sounds or create music, but it captures something true about patterns and rhythms in orbital dynamics. Foreshadowing the 2052 supermoon creates continuity in the narrative. These alignment events and close approaches mark time in ways that transcend individual human lifespans. Someone born in 2040 will be 12 years old when the supermoon occurs, will be 20 when Apophis makes its close pass, will be middle-aged before the next major planetary alignment. These cosmic events provide waypoints in generational memory, shared experiences that define eras and give structure to historical time beyond human constructs like decades and centuries. Part 13. The moon that touches Earth. November the 9th, 2052, will bring the closest lunar approach of the 21st century, a supermoon so supra that it strains the definition of the term. The moon's orbit around Earth is not circular, but elliptical, meaning the Earth-Moon distance varies from about 363,000 kilometers at perigee, closest approach, to about 405,000 kilometers at apogee, furthest distance. This variation in distance causes variation in the moon's apparent size as seen from Earth. When the moon reaches perigee during its full phase, appearing at its largest and brightest, we call it a supermoon. The November 2052 supermoon will occur at an exceptionally close perigee, bringing the moon to approximately 356,500 kilometers from Earth's center. This is roughly 3% closer than typical supermoons and about 6% closer than average full moons. The distance might sound trivial in percentage terms, but remember we're comparing angular sizes, which depend on distance in nonlinear ways. A 6% decrease in distance produces about a 13% increase in apparent diameter, and about a 30% increase in apparent brightness. The moon will appear large enough at this closest approach that the size difference from average full moons becomes noticeable even without instruments. Place a full moon photograph from 2052 next to one from an average lunar distance, and the difference is obvious. The supermoon fills more of the sky, its features appear larger, its brightness illuminates landscapes more dramatically. Under ideal atmospheric conditions with the moon near the horizon, the combination of actual size increase and moon illusion, the psychological effect that makes horizons moons appear larger than overhead moons, will create views that seem almost surreal. Photography opportunities will be extraordinary. Lunar photographers wait for supermoons to capture the moon alongside landscape features, using the moon's increased size to create dramatic compositions. The 2052 event will provide the ultimate opportunity for this generation of photographers. Planning will start years in advance, scouting locations where the moon will rise or set behind interesting foreground subjects, calculating exact timing and positioning to get the shot. The brightness boost carries consequences beyond aesthetics. Moonlight in general is bright enough to cast shadows and affect nocturnal animal behavior. Supermoonlight is brighter still, potentially casting distinct shadows from objects and illuminating landscapes to levels approaching twilight. Nocturnal animals that time their activities around lunar phases might respond to the unusual brightness. Predators that hunt using vision might have advantage over prey that rely on darkness for concealment. Prey species might alter their behavior, staying hidden during the brightest hours. Extreme tides represent the most significant physical consequence of close lunar approaches. Ocean tides result from gravitational gradient, the difference in Moon's gravitational pull on the near side of Earth compared to the far side. This gradient creates two tidal bulges, one facing the Moon and one opposite, and Earth's rotation carries coastlines through these bulges, producing the familiar twice-daily tidal cycle. The strength of tides depends on the Moon's distance, with closer moons creating stronger gradients and therefore higher tides. Spring tides, the highest tides occurring during new and full moon, when Sun and Moon align, will be amplified during the 2052 supermoon. Coastal areas already experiencing high spring tides will see water levels several centimeters higher than usual. This might not sound dramatic, but at high tide during storms, those extra centimeters can mean the difference between water staying in channels versus overtopping seawalls and flooding coastal infrastructure. Coastal flood warnings will likely be issued for vulnerable areas, particularly those already dealing with sea level rise from climate change. Seismic coupling speculation enters murkier territory. Some researchers have explored statistical correlations between lunar phase and tidal forces with earthquake occurrence, looking for evidence that tidal stress on faults might trigger earthquakes that are already close to failure. The mainstream consensus is that any such effect, if it exists at all, is negligibly small. Faults fail when accumulated tectonic stress exceeds friction holding them locked. Tidal stresses are orders of magnitude weaker than tectonic stresses. However, for faults already at the threshold of failure, even tiny additional stresses might theoretically provide the trigger. Studies have found weak correlations between tides and earthquakes in some fault systems, but not others, with effects so small they're difficult to separate from statistical noise. The 2052 supermoon will provide a natural experiment. If tidal triggering is real and measurable, we might expect slightly elevated earthquake rates globally during the days around closest approach. If rates remain normal, it further supports the conclusion that tidal effects on seismicity are negligible. Cultural response to the supermoon will likely include both celebration and anxiety. Festivals and public viewing events will draw crowds to dark sky locations and famous landmarks. Lunar eclipses, when they coincide with supermoons, become media spectacles attracting millions of viewers. Even without an eclipse, the record-setting nature of the 2052 event will generate interest. Simultaneously, various doomsday predictions and apocalyptic interpretations will circulate online, claiming the close approach portends disasters. These predictions follow predictable patterns and will be equally predictably wrong, but they'll briefly attract attention and cause unnecessary anxiety among people unfamiliar with astronomical facts. The phrase "the night that glowed like day" exaggerates, but captures the qualitative experience of extremely bright moonlight. Human eyes adapt to darkness, pupils dilating to gather more light, photoreceptor cells increasing sensitivity. Under full dark adaptation, the sensitivity range of human vision spans many orders of magnitude. Moonlight on a typical full moon provides enough illumination to walk comfortably, read large print, and see colors vaguely. Supermoonlight pushes this further, potentially allowing reading of normal print and seeing colors more vividly. Combined with high atmospheric clarity and dark surroundings, the experience approaches the illumination level of deep twilight. Atmospheric scattering studies benefit from bright moonlight because lunar illumination provides a stable light source for measuring atmospheric properties. Research groups studying aerosols, clouds, and atmospheric chemistry sometimes use moonlight as calibration or to extend observations beyond daylight hours. The supermoon provides unusually high signal levels, potentially allowing more precise measurements or detection of subtle effects normally below detection thresholds. Citizen science projects could coordinate global observations of the supermoon, collecting data on apparent brightness, color, and atmospheric effects from observers worldwide. Similar projects have successfully collected eclipse observations, meteor counts, and aurora reports, building datasets that supplement professional observations and engage public interest in astronomy. The supermoon offers an accessible target that anyone can observe and photograph, lowering barriers to participation. The transition to discussing comets that may outshine even this supermoon sets up the final narrative beats. The moon at its closest approach will be spectacular, but it's a regular phenomenon, the closest of a continuous series of supermoons that recur monthly in varying degrees. Comets represent wild cards, unpredictable visitors that occasionally rival or exceed the moon in brightness, but do so rarely and without reliable schedules. The comparison highlights different types of cosmic phenomena: the predictable cyclic motions of bodies locked in regular orbits versus the chaotic, punctuated appearances of comets falling from the outer darkness. Part 14, 2060, the brightest comet ever. In 2060, something is going to happen that no living human has ever witnessed. The forecasts are already in, the orbital calculations already done, and astronomers are marking their calendars for an event that will rival anything in recorded history. A massive object from the Oort cloud, that distant reservoir of comets surrounding our solar system, is heading toward the inner solar system on a trajectory that will bring it close enough to the sun to become spectacular. Not just bright, not just visible, but potentially as luminous as the moon itself, dominating the night sky for weeks or possibly months. If the predictions hold, this comet will be the astronomical event of the century, a once-in-a-lifetime spectacle that will be visible even in daylight, casting shadows at night, and fundamentally changing humanity's relationship with the sky for everyone alive to see it. Let me put this in perspective. Most comets that pass through the inner solar system are faint, requiring binoculars or telescopes to see. A handful each decade become visible to the naked eye, appearing as fuzzy patches of light with modest tails. Every few decades, we get a bright comet, something that makes headlines and draws people outside to look up. Comet Hale-Bopp in 1997 was one of these, visible for over 18 months and bright enough to see easily from cities despite light pollution. Before that, Comet West in 1976 put on a spectacular show for those who woke up before dawn to see it. And of course, there's Halley's Comet, which returns every 75 to 76 years and has been documented by humans for over 2,000 years, appearing in Babylonian records, Chinese chronicles, and the Bayeux Tapestry. But even Halley's Comet at its best is just a bright comet. It's impressive, sure, but it doesn't dominate the sky. The 2060 comet, if it lives up to its billing, will do exactly that. Current models suggest it could reach an apparent magnitude of -10 or even -12, which would make it as bright as a half moon or possibly a full moon. To understand what this means, you need to know that the magnitude scale is logarithmic and backwards. The Sun has an apparent magnitude of -26.7. The full moon is -12.7. Venus, at its brightest, is about -4.9. A bright comet like Hale-Bopp topped out at around -1. Each step represents roughly 2.5 times more light, so a magnitude -10 comet isn't just twice as bright as Hale-Bopp, it's thousands of times brighter. What creates a comet this spectacular? Size matters, obviously. The nucleus of the 2060 comet is estimated to be absolutely enormous, possibly 50 to 100 kilometers across, making it one of the largest objects ever to visit the inner solar system from the Oort cloud. For comparison, the nucleus of Comet Hale-Bopp was roughly 60 kilometers across, and that was already considered huge. But size alone isn't enough. The comet also needs to pass close to the sun, close enough that solar heating vaporizes massive amounts of ice, creating a coma that can grow larger than Jupiter, and a tail that can stretch for hundreds of millions of kilometers. The 2060 comet checks all these boxes. Its perihelion will bring it within about 0.3 astronomical units, roughly 45 million kilometers, which is inside Mercury's orbit. At that distance, the sun's heat will vaporize not just water ice, but also more volatile compounds like carbon monoxide and carbon dioxide. But beyond the science, there's something deeper happening here. For one brief moment in 2060, humanity will share a common experience. People in every country, on every continent, will look up and see the same thing. A comet so bright it can't be ignored, so spectacular it transcends language and culture and politics. The 2060 comet will be impossible to miss. It will dominate the twilight and nighttime sky, visible even from brightly lit cities, casting enough light to read by if you're in a dark location. And here's where things get interesting, and maybe a little unsettling. What happens when you introduce a light source into the night sky that rivals the moon? We know that moonlight affects ecosystems. Nocturnal animals adjust their behavior based on lunar phases. Predators hunt differently during full moons. Human circadian rhythms, the internal clocks that regulate our sleep-wake cycles, are influenced by ambient light levels. For the entire time humans have existed, the moon has been the brightest object in the night sky. What happens when we throw a third variable into that equation? The truth is, we don't know. The comet will be visible for weeks, possibly months, and during that time it will be pumping light into the nighttime environment at levels Earth hasn't experienced from a comet in recorded history. Now, let's talk about the less pleasant possibilities. Whenever a comet gets this close to Earth, people start worrying about impacts and catastrophes. Let me be clear, the 2060 comet is not going to hit Earth. Its orbit is well characterized, and it will miss us by millions of kilometers. But that doesn't mean it's completely harmless. Comets shed material as they approach the sun. Dust, small particles, sometimes even larger fragments break off and spread out along the comet's orbit. If Earth's orbit happens to intersect the comet's orbit after the comet has passed, we could encounter this debris stream, creating a spectacular meteor shower. But there's a more concerning scenario that, while unlikely, isn't impossible. Comets sometimes break apart as they approach the sun. The thermal stress, the tidal forces, the outgassing pressure, all of these can cause structural failure in a comet's nucleus. If the 2060 comet were to fragment, and if one of those fragments happened to have an orbit that brought it closer to Earth than predicted, we'd have a problem. The odds are extremely low, but it's not impossible. This is why asteroid and comet tracking has become such a serious endeavor. But hopefully, the dominant response will be awe. Because whatever else it is, the 2060 comet will be beautiful. It will be a reminder that we live in a universe capable of creating spectacular phenomena. For a few weeks or months, dinner conversations will include discussions of tail structures and coma dynamics. Children will stay up late to see the comet. It will become part of the cultural fabric of that generation. And when it's over, when the comet has swung around the sun and is heading back to the outer solar system, we'll be left with photographs and memories. But even as it fades, there's another date on the cosmic calendar that represents an equally profound milestone. Part 15, 2177, Pluto's first birthday in cosmic reflection. On February 18, 1930, a young astronomer named Clyde Tombaugh was examining photographic plates at the Lowell Observatory in Flagstaff, Arizona. He was searching for a predicted ninth planet, a world beyond Neptune that might explain slight irregularities in the outer planet's orbits. The work was tedious, comparing pairs of photographs taken days apart, looking for anything that moved against the background of stars, and then he found it, a tiny dot that had shifted position between exposures. Planet X, the ninth planet, Pluto. The discovery made headlines around the world. Pluto was the first planet discovered by an American, and it captured the public imagination in ways that astronomical discoveries rarely do. The name Pluto, suggested by an 11-year-old girl in England named Venetia Burney, seemed perfect. The god of the underworld for the distant, dark world at the edge of the solar system. For 76 years, school children learned that the solar system had 9 planets, and Pluto, tiny and mysterious, was the last outpost before the great darkness of interstellar space. And then, in 2006, the International Astronomical Union redefined what it means to be a planet. Pluto met 2 of the 3 criteria, but failed the third. It hadn't cleared its orbital neighborhood of other debris. Under the new definition, Pluto was reclassified as a dwarf planet, and the solar system was back to 8 planets. The demotion was met with surprising public outcry. People felt affection for Pluto, this distant, underdog world. But here's something that puts all of this in perspective. In 2177, 247 years after its discovery, Pluto will complete exactly 1 orbit around the Sun. It will return to the same position in space where Clyde Tombaugh first spotted it on those photographic plates. Think about what that means. Pluto's year, the time it takes to complete 1 orbit, is 247.9 Earth years. When Pluto was discovered in 1930, it had completed about 36% of one orbit since the Declaration of Independence was signed. We discovered Pluto, studied it, sent a spacecraft to fly by it in 2015, watched it get demoted and debated and argued over. And through all of this, Pluto hasn't even made it once around the Sun. This is a profound lesson in timescales. We humans live, at best, about 80 to 100 years. That's the span of direct memory and experience for any individual. Our civilizations last longer, with continuous written records going back about 5,000 years. But even on that scale, Pluto has completed only about 20 orbits. The entire span of human civilization covers just 20 trips around the Sun for this distant world. And if we zoom out further to the 4.5 billion year history of the solar system, Pluto has completed roughly 18 million orbits. That sounds like a lot until you realize that Earth has completed 4.5 billion orbits in the same time. But it's not just Pluto. The outer solar system operates on timescales that dwarf human experience. Neptune takes 165 years to orbit the Sun. Since its discovery in 1846, Neptune has completed barely more than one orbit. Uranus takes 84 years. Saturn takes 29. These are worlds that move through the zodiac at a stately, almost imperceptible pace. Ancient astrologers only knew of 5 planets beyond Earth because those are the only ones that move noticeably across the sky within a human lifetime. And this raises an interesting question. What's the longest timescale that humans can truly comprehend? We can intellectually understand that the universe is 13.8 billion years old, that the Sun formed 4.5 billion years ago. We can recite these numbers, put them in textbooks, teach them to students. But do we really grasp them? Can any human mind truly hold 13 billion years of time in its head, in a way that feels real? Probably not. Our intuition is calibrated to human lifetimes, to the span of years we expect to live. Beyond a few generations, time becomes abstract. This is why Pluto's first birthday since discovery is such a poignant marker. It's a timescale that's just barely comprehensible to our civilization. 247 years spans from 1777 to 2177, over a century and a half in our future. It's longer than any human life, longer than most institutions survive, but short enough that we can trace cultural continuity. People in 2177 will be able to look back at records from Pluto's discovery and understand what those astronomers were doing and why it mattered. But when Pluto completes that first orbit in 2177, it will just be beginning its second orbit since discovery. And that second orbit will take another 247 years. Pluto won't complete a third orbit until 2671. The people who will witness Pluto's second birthday haven't been born yet and won't be born for centuries. And by then, will humans still care about Pluto? Will we still be watching the skies, tracking the planets, marking these cosmic milestones? I'd like to think we will be. Despite everything, despite the chaos that often characterizes human behavior, we've maintained astronomical observatories for centuries. We've kept records, passed down knowledge, built on the discoveries of previous generations. The fact that we can calculate Pluto's orbit and predict its position in 2177 is a testament to the power of accumulated knowledge, of humans working across generations toward common goals. And speaking of long timescales, consider this. When 3I Atlas entered our solar system in 2024, it had been journeying through interstellar space for millions of years. If it was ejected from a star system 10 light-years away, traveling at 66 kilometers per second, it would have taken about 45,000 years to cover that distance. During that entire time, this comet was frozen, unchanged, drifting through the void. And then it spent a few months in our solar system, got destroyed by the sun, and was gone. But understanding isn't the same as experiencing. We can calculate Pluto's orbit, but we can't feel what it's like to take 247 years to circle a sun. We can measure the sun's lifetime at 10 billion years, but we can't viscerally grasp that span of time. We're bounded by our biology, our mortality, our place in space and time. When Clyde Tombaugh discovered Pluto in 1930, he was 24 years old. He died in 1997 at age 90, having lived to see spacecraft visit every planet in the solar system, to see humans walk on the moon. But he never saw Pluto complete an orbit. No human who was alive when Pluto was discovered will live to see its first birthday. That milestone will belong to people not yet born.